Thank you very much for the kind introduction. I'm very happy to be here, guys. I heard that you guys also are the field from power electronics. So I had a lot of slides in the beginning that was quite basic. So I maybe go through quite fast and go maybe to the most interesting part. So, of course, we cooperate already. And what I wanted to show here is roughly the area of research that we have it in our group. So I will start it mostly give a little bit introduction about our group in University of Twente. We are a relatively new group. 5 years ago, we were created. We're going to go through that. And then the power electronics basic, I can imagine that I can bypass that, right? Because you guys know a little bit already. And what I think is more important for this presentation is exactly what I see the design and performance trends. Those define our core research. So what I'm going to show you is with a lot of support material, especially for Infineon, presenting how semiconductor has been developed. And our research, especially in circuit topology modulation, follow that trend. So we try to combine the latest performance trends in semiconductor and bring that to the circuitry design and the way that we operate it. And then I'm going to focus in the application that we are mostly working on, in the e-transportation, especially in battery charging. So our university focuses mostly research in battery. Of course, we are from the power electronics group, so we do work in the electronics of it. I mean, Prashant, on Monday, he's going to have a lecture about the battery research and the smart BMS systems. And I'm going to just give 2 examples of how the trends of the semiconductors and the challenges of the application affected our own research line. So we just select two PhD students research to present it. And then if you have any question, of course, we have much more in the application. If you're interested, we can always talk, and then we can exchange information if you want it. Yes, so maybe I was already introduced, but then I can go fast. So I'm originally from Brazil, but I'm also Dutch. I'm happily married, 3 kids. I think part of good research is to have a good life, personal life, and support of the family. I'm lucky for that. I don't know why, but I was born in this beautiful island in the south of Brazil. You guys also live in a nice country. I don't know why I left that country. I really like it. And especially this island is very beautiful, very nature-oriented, a lot of green, a lot of adventures. But then I came to study in Switzerland, where I did it, I was part of Johan's group. Johan's retired now. I don't know what's going to happen to the power electronics group there, but used to be one of the top 1 in Europe. So I live in Switzerland for 10 years, and I work as a senior scientist at the ABB Computer Research Center, where I was mostly working in the traction business. It's mostly battery chargers and auxiliary power supply for the traction business, but also for the solar. So I was working with, especially in ABB Italy and Finland, with the utility scale solar application, really megawatt systems. And then opportunity came to become an academic. Then I joined TU Delft in the Netherlands, where I worked for 4 years. I was assistant professor, then became associate professor. And my main area of research was battery chargers. And then I decided to go back to industry. I went to the European Space Agency. I was a technical officer. I was working mostly in project management there. And then I decided to go back to academia again, and a professorship opened. Then I joined University of Twente since 2022. Yeah, just roughly I've been swinging by industry and academia. I think for power electronics especially, it is, we need to be close to industry, right, to be relevant in this area. Yeah. Let's talk about Twente, University of Twente. University of Twente is one of the 4 technical universities in the Netherlands, what they call 4TU. And we are considering the Netherlands the most enterprised university in the Netherlands. So the core of University of Twente is really to do research, I would say. If you see the number of students that we have, it's typically about 13,000, and number of academics is 3,200, right? So you have a factor of 4, right? So you can see that number of academic staff and number of students is quite close. And if you go to the electrical engineering, there are more staff than students. So you can already see that most of our revenues come from research, not from education. The university has a lot of spin-off companies. There's a lot of in the campus around. There's a lot of SMEs. They do quite advanced research for military, space, in other areas. A lot of things about biomedics there as well. We see some buildings there. We see Tech Med Center. They are very active, also like you guys. A lot of things you showed us is also what our colleagues do. These smart sensors from biomedics, embedded actuators, those things. It's a lot of research in that area. But also battery. A lot of research in battery. We are very close to Germany. We are in the border. And Northwest Germany strategically is the area where they develop research in battery in Germany. So if you go to Münster, it's one of the main universities for material research. And with also Aachen in the south, they do more the power electronics and also the cycle of cells. So, and in this border is where we intersect. We have about 20 research groups for battery and about 70 staff work in that field, but also solar. Our university is very strong in microelectronics as well. I saw also what you guys do is similar what also our colleagues do there. And University of Twente also, within the Netherlands, has been winning several times the best program for electrical engineering in the country. Although we have more renowned international universities, but internally, Netherlands has one of the best programs for education. So they really value also, courses are given if they mean something, right? Not just create a lot of courses where the number of students not so high, right? Yeah, so briefly speaking, and then in the Water University ranking, we are the first. We'll be ranked from 2021 in 2025, globally, the most innovative university. Right? So that said, it's really about research. It's really about pushing the boundaries of research, especially in this area of microelectronics, biomedics, battery, and so on. But we are relatively new in that area. So I don't know if you heard, but Professor Bram Ferreira, he was a very famous professor in power electronics. He was a fellow at IEEE, and he was also a PELS Society president. He was a professor and head of the power electronics group in TU Delft. So when I joined TU Delft, he was there, and then we worked together. And then was an opportunity for open a new group in this university. And he moved there, so in 2019. So I joined TU Delft in 2018, and 2019 he moved to University of Twente to open this new group. So there was a strategic funding for the university, for the country, just prior COVID, to really develop areas to make Netherlands competitive for the future markets, right? And power electronics for that region there close to Germany, that was mostly focused on microelectronics and materials. They saw the opportunity to also move into systems, and that's why power electronics was created. And the good thing for us that the country is relatively rich, right? Netherlands is really an innovative country. You may heard some of the companies that we have there, ASML, right, for devices. We also have Philips and all the big companies. So they really invest in research, and that's why in very little time we managed to grow our group in 25 PhD students. So we do have, in reality, academic FTE only 4.5, but we do have a lot of PhD students and postdocs. So we do focus in those pillars, power electronics, that's myself. We also do smart grids in energy access, that is Helena. Smart grids for energy management system is Natalie. Measurement system is Professor Rietveld. Battery-enabled system is Prashant. You're going to hear something. But we also do power device and packaging. That's Ray Routing. Yeah, so this is roughly the story of our group and university. So these, you can see the faces, the people that I said it. So as I said, the academic staff is 6, but also those 6 2-apart times, right? So Yelena and Hertz, they are just few days in a week. The permanent staff is just myself, Ray, and Natalie. I think you guys, some of you met Natalie before. She came here a few times, right? I think at least once. And Prashant. This is the faces of the PhD students that we have it and postdocs. Yeah, we are currently, some of them already left, so the ones started is, I think these photos are from 2025, right? So need to be updated a little bit. But we are a similar size, so we're reaching 30 PhD and postdocs. Yeah, so what we do there? So our research focuses in research and development of safe integration of efficient, reliable, intelligent power electronics. So we see power electronics as a more active device in a system, right? So we see that we need to incorporate the disruptive technologies, and that means new semiconductor technology in packaging devices, and we need to make it sure that those guys work reliably in converters, right? So we need to design systems that aggregate the values that the application need. It can be efficiency, cost, reliability, power density, weight density, and so on and so forth. But also we know that the power electronic circuitry, they do have active role in the system, right? So if you have in a multi-energy system, as I just showed in the battery, solar, fuel cells, electrolyzers, and this example is actually for sustainable fuels, so how to generate sustainable fuels. You'll see that you can, each block to integrate, need to be integrated to each other. So converters can be used there. And then when you see different type of generation, different type of energy storage, you also need some sort of smart energy management, right? So the power electronics enable that intelligent energy management. But also during performance, you wanted a system to operate during his whole lifetime with some key performance. So you wanted the total cost of ownership of a system to be low as possible, right? So you wanted not only initial costs, but also operational costs, preventive maintenance, and so on. So we do a lot of research about state of health monitoring and prediction to make sure that the lifetime performance are improved. In the case of Prashant, he does that for battery cells and strings. But we also, in case of Ray, we also do for semiconductor devices. We also do for capacitors, supercapacitors, right? So those are key elements that fail in a system, right? Capacitors and semiconductors, they are the weakest point if you compare, right? Of course, inductors is passive element. Typically, as soon as you don't have so much mechanical stress, it lasts for a long time, right? Good. So basically, we go from devices to optimization of components, to system integration and lifetime performance. That is our goal. And each one of our academics have a key role in each one of those stages. And of course, we cooperate to each other a lot. We do a good, we like working among ourselves, and we cooperate because we know that our strength is in the intersection of these layers, right? We do have a lot of projects, a lot of partners. I list here some of the projects that we have it. So we have about 40 projects. Each project is sponsored at least one PhD student. We do have a lot of external cooperation as well with external PhD students, external partners. Yeah, most of our funding comes from the Dutch government. NWO or RVO are the key sponsor of our research, but we also rely on Horizon and direct funding from industry. This, again, the list here need to be updated. I think we are, for sure, some of them ended and some new ones have started. Good. So, base of power electronics. I don't think I should go too much in details here because if you guys already know, I can go briefly. As you know, power electronics is an interface between whatever there is electrical energy processed is being done by a power electronic circuitry, right? So if you generate energy in any form from a hydropower plant, a nuclear power plant, solar, wind, and even combustion, diesel, eventually that needs to be converted in a way that the load wants, right? So if you have a smartphone, that guy needs to be charged, and the battery is DC 5 volts, right? So you know the outlet's 230. So that means you need at least to have one power conversion stage from AC to DC, and also need to have a large voltage step. This is typically done in two-stage system, AC-DC, DC-DC, with a galvanic isolation, and this is done by a power electronic circuitry. And that's play a big role in future grids, especially when you start to decentralize the system, right? And that's what I show here. We show the unifilar diagram of future grid, where we have the generation on top, and eventually that generation, independent if it's AC or DC, eventually becomes AC. And if you want to transmit the power for long distance, you may consider HVDC. And then you transmit close to the load, and eventually come from the high voltage to the medium voltage, and then for a transformer, and eventually becomes a low voltage for another transformer. And then close to the load, you have the decentralized generation of wind, solar there. We have the charger for the EVs, and for your homes, you have also plugs, and then you have electronics there connected. So each one of these pink block is a power electronic circuitry. And if you think about the needs of energy, it's predicted that in 2050, we need 20 terawatts of energy. And because of this energy, a lot of them are going to be generated for the decentralized generation systems. We need a lot of battery energy storage, about 15 terawatt hour of energy storage to make sure that the congestion are well dealt. It's predicted in such a scenario, every power will be processed by 4 power electronics conversion stage. So that means we need, if you have 25 terawatts of energy generated and consumed, we need at least 100 terawatts of electronics installed. And that's very challenging because electronic doesn't last long, right? So every 20, if you put electronic lasting 20 years in average, of course there are applications like trains that electronics last maybe more than 30, 40 years, but in average 20 years, we need to replace the whole grid every 20 years. So there is a lot of waste, electronic waste, where the circular economy play a big role. That is a very heavy topic today, right? But show also the relevance of the subject for society in general, right? It's cybersecurity, all those matters is very important for us, right? Yeah, so my objective here is to show that power electronics is everywhere. Wherever there is electrical energy being processed, generated, consumed, transmitted, it is processed by a power electronic system. So if you guys are doing power electronics, you are in the right subject for jobs, for sure, and societal relevance. I'm not going to explain what's a DC-DC converter, so I can bypass here, because those I put here just because I will discuss sometimes DC-DC, DC-AC, and if you were not familiar with the topic. But anyway, DC-DC is a normal chopper, AC-DC is rectifier, DC-AC is an inverter, and AC-AC is a cycle converter. And different applications, they use different blocks. Power electronics with what they call switch mode electronics, right? So we really rely on semiconductor devices, passive and actives. And these guys operate like a mechanical switch, on and off, right? So that's what switch mode electronic is. So when the device is on, you want very low impedance. When the switch off, you want a very high impedance, right? So really open. And what we do is we get energy from the source. We store in passive elements, in this case, big capacitors and inductors. And then we release that energy in a controlled manner to the load. And that's how power conversion is done. And this is done today with microprocessors. Electronics develop a lot in the past 30, 40 years. And then intelligence becomes available because we have these powerful devices. And we can do so many things on that. Yeah. Power electronics is definitely multidisciplinary, as you already know. We need a lot of different components. Each component have different technologies, different materials. Different materials create different metrics. Different materials have different costs, different weights, different sizes. So that brings a lot of layers of optimization, right? Semiconductors, there are different technologies. Each one behave differently. They have different loss performances. Different loss need different thermal management. So the selection for power devices is always very important for us. And we also need a lot of other auxiliary circuitry, relays, fuse for protections, right? Varistors for suppression. The analog electronic, linear electronics for conditioning and monitoring. As already said, the microprocessor for intelligent application. Yeah, this is the history for us. Power electronics starts really when the electronics developed, right? Diodes, active controllable diodes came into the market in the 50s, where power electronics really developed. And when they develop, we need circuitries, we need techniques to improve the performance of the system. Before the losses are so high, then that's why in the 670s, soft switching techniques were invented, resonant converters there, right? So a lot of research in that field. TU Delft was already very famous for soft switch topologies. Professor Schwartz was the one that invented the resonant converter. Microelectronics developed modulation techniques really to overcome the challenges of the semiconductor. They were pretty much not as good as today, right? So then you need to make sure that you could handle thermically. So you need to be very creative in the way that you operate this guy. And then that's why different topologies came into market and different way to operate them. In the 90s, especially, semiconductor developed really a lot. Superjunction and wide bandgap device, they came to the market, so you could bring the active device into high voltage applications, right? And then, it was really explosion of development in semiconductors. Also, microprocessors become low cost, right? So they could start be used in products, right? Telecommunication system develop a lot. Improved of modulations and data acquisition. So more knowledge you have it, more you can do, and more processing capability you have. It enables you to improve the performance a lot. Eventually, the technology matured enough to really allow us to push the boundaries, the technology, right? So we push the operating frequency of this guy very high, and then thermal management and the parasitics in the system become very critical to the operation. That means today, a lot of research goes into packaging and thermal management, right? I think there's a clear development there. And again, intelligence is also come there. It's the state of health monitoring to predictive maintenance, to identify faults before they happened. In key applications, especially in transportation, in aerospace, is there. So a lot of development, and especially the past 20, 30 years, it was a big revolution. Not anymore in circuitries and modulation strategies, but really how to push the boundaries of each technology. Yes, applications, industrial applications, always been the driver of power electronic development, especially in motor drives, telecommunication systems, power supplies in general. But eventually in the 90s, renewable energy came, solar cells become more reliable and low cost, wind, fuel cells, they exist, all this technology exists so long, but they were not yet, they were too expensive to be used widely, right? Now they have become affordable. Solar is one of the lowest cost of power. I think today, if you see the cost per kilowatt is amazingly low. It's unbelievably low, so it's really affordable. But electric transportation in the past 20 years really developed. I talk about cars, ships, submarines. They were electric for 200 years, right? So batteries, I mean, most submarines, they use battery, right? Or nuclear propulsion or those things, but they anyway need battery there, right? So electric machines, actually the first car was electric, it was not combustion, right? When combustion came and cost of fuels were so low, and then they become the stream because they were much cheaper than electric, right? But anyway, so in the 90s and especially 2000 and something, when the real cost of EV become lower for us, then it's exploding pretty much, right? Also, with the explosion of renewables, energy storage become very important, because if the percent of renewable energy become more than 20% in the whole energy mix, it is important for the reliability of the grid that you can do buffering, right? So that is why hydrogen in batteries there was a strong push in those technology, and that's why the cost also drastically reduced. And with amount of electronics there and application requiring a lot of reliability, digitalization become a big thing. Now you can do digital twinning, machine learn, AI that can get a heavy amount of data and then do prediction what's going on to the system, right? They can give you instructed ideas how to operate the system in a way that you can extract the maximum performance of the system and the components in that system. So digitalization is really the future, and I think those processes are only enabled because we have a power electronics that can be can take a big role in the system, right? So because it is the one that processes most of power, right? So then you can give flexibility for the system. Yeah. I tried to be fast, but actually it took too long. Okay, now I'm going to explain to you what I see the trends. It's not me that decide this. It's what you see in the literature, right? So this is a figure I took from Infineon. As I already mentioned, power electronics is highly dependent on semiconductor technology. And one of the key problems that we have when we push the boundaries of the technology is how to manage losses, right? And what you see here is pretty much the ADES-on per chip area of different semiconductor technology according to the rated blocking voltage. This is done by Infineon. The points are the device that are available commercially, and the lines are the analytical model that they have. So you can see that the models they have match what they can manufacture. That tells you that the manufacturing of the device is mature, right? So then, especially for silicon-based devices, you can see that they can manufacture what physically is possible, right? But when you go to wide bandgap device, that's not necessarily true because manufacture is more complex. And then yielding gets limited, right? But anyway, if you compare these curves, you see, okay, you know the conduction loss is proportional to the ohmic resistance of the device when the device is on, right? So the lower the ohmic resistance, better it is for losses, right? Because it's always RMS square, right? And you see, based on this curve, is when you, from the physics of the device, the highest blocking voltage you have it, highest will be the losses. And this is log, right? So you see a linear in the log, that means it's exponential, right? The growth. So what does it mean, this? It means that if you have a 1200 volt device, a single one, the losses will be higher than if you have two of 600 volts in series. And this is very important for power electronics because it enables you to use multi-level topologies, right? So giving you an insight that puts unipolar devices in series for series cascade multi-level makes more sense than low number of devices, right, for the same blocking voltage. And multi-level topology also have all the benefits, not only losses, right? You can also reduce filter size and everything. So then enable you to really push to more complex systems because that bring a lot of benefits for you. And that's a key point. And if you compare the physical limits between silicon technology that's quite mature and wide bandgap devices, you see for the same chip area, a silicon carbide device can be 10 times better than a silicon for the same chip area. If you go to GaN, this potential can be even 20 times. So less losses, simple thermal management, right? Then you can also operate in high frequency, so you can reduce passive filtering for power quality better. So then that really allowed you to really push the technology much higher. And application where require efficiency, power density, cost are benefiting from this. That means if you do see today power electronics, I mean, we talk about wide bandgap devices. It's clear the way to go, right, in terms of performance. If you really push for application requiring performance, wide bandgap, yeah, it is there. Yeah, so this. Another thing is, if you compare, let's say in the left-hand side, you have the VI curve during the switch-off transition of a silicon IGBT for 100 amp application. And in the right-hand side, you have the same curve for a 100 amp SiC MOSFET device. So you already clearly see in the figure, for the same current rating, the chip area is much smaller from the silicon carbide perspective. That's what exactly the previous graph was telling you, right? That for the same RDS(on), I can have a factor of 10 reduction. Of course, in this case, it's not the case because we have silicon carbide is not yet mature technology for manufacture. The yield is very low, so they do conservative, right? Make sure that when they manufacture a wafer, most of the devices can be used. But as soon as technology evolve in the future, then for the same current rate, it will be smaller, smaller, and smaller. And the smaller the chip is, faster we can switch, right? Because the parasitic capacitance in the chip define the speed. Even in this conservative design, the speed of a silicon carbide MOSFET compared to IGBT can be 10 times faster. And you know the losses, switching losses, is the overlap between voltage and current, right? So when you do instant product between voltage and current, that's where the losses are. So shorter time, less loss it is. And that's why wide bandgap device can be used in very high frequency applications, right? But create all the limits, right? And you can already see in the blue curve, there's an over voltage, right? In the silicon carbide device. That's because the parasitic of the commutation loop affects a lot the performance. That's why there's a strong push for development for better packaging of those devices, right? Because you need to minimize this parasitic inductances there. And that's over voltage that creates a lot of issues for EMI. If there's DVDT, create a lot of common mode current in machines, so that degrades the insulation. So there's a lot of key challenges there, right, that need to be overcome. Yeah, and also because the chip is smaller, the thermal resistance becomes higher than a bigger chip, right? So the thermal issue becomes more complex as well. As I said in the beginning, that when you go in development of power electronics, packaging and thermal management become key in applications that we have today. And that's where you see most of research, this moment, especially for the transportation, it is in how to improve the performance of the power module. Now I am showing the figure of merit when you put together conduction and switching loss. So the RDS(on) is the static conduction losses, and Q or SS is the energy in the parasitic capacitance of the device. When you do a figure of merit like this, bigger, the better it is. So it's like a trade-off between conduction and switching losses. And then you see here a plot from my former supervisor, where you have a lot of the points there are the the commercial device available, and the line that you have there is actually the extrapolation, right, of the curves, right? So you have again the rated voltage of the device base, and then the Y, the figure of merit. And you see for GaN, of course, the devices are mostly in the low voltage area, right? So you see the red points there. They are much better than the silicon, right? And the silicon carbide, mostly for high voltage application, they're also much better than the silicon. So you already see the future shaping in a way that wide bandgap device, it's eventually when the cost reduces, especially, they're going to replace in many medium to low power applications the silicon. Performance is far much better. And you can also see a big push of GaN become available in higher and higher voltage. So it's predicted that the 600 volts application, even 1200 volts application, GaN is eventually going to dominate. As we saw before, also for conduction switching performance, it overcome also silicon carbide, right? So, but unfortunately, because of the technology, you cannot do very high voltage. So in medium voltage application, the silicon carbide will dominate. Or low voltage, but much higher power application, silicon carbide will be. Yeah, so again, low voltage class, as I said before, to build higher voltage switches become very, very interesting because of this, because then you can have not only conduction loss, but switching loss performance, right? So in application where you need to really push power density, weight density, we see especially GaN technology going very high. That's why a lot of research in multi-level topologies, right? And this is, they did a comparison which technology we're using in EVs in 2021 and what they predict in 2027 to be. And they compare silicon carbide MOSFET in discrete or power modules, packaged in discrete devices, TO247, or in advanced modules. And then also GaN HEMT, and also silicon MOSFET in silicon IGBTs. And you can clearly see in the beginning, because of course mature technology, the power modules with IGBTs are mostly used for the traction, right? For the charger, and this combines not only the traction, but also the charging, onboard charger of the vehicle, right? Very few use of GaN, 2021, some use of silicon carbide, especially for the charger, but IGBT still was dominant for the traction. But now in 2027, silicon carbide power module become dominant for the traction, and GaN is predicted to be mostly used for the onboard charger because, okay, power density and the power processing normally up to 20 kilowatts, right? So then GaN exactly will be dominating that market. Yeah. And just this is a visual prediction from Infineon where silicon carbide, silicon, and GaN are going to be used. And that the X is the frequency operation, so high frequency exactly for power density, right? Or weight density application. And low frequency for high power application. Silicon, you dominate. Medium power, medium frequency, silicon carbide, most likely you're going to dominate. And medium to low power, GaN, and very high power density, you dominate. So they will still be in the market. One key aspect as well, I think your colleague already presented to us, one of the key challenges is protection, right? So what you show here, if you get in the same package, 1200 volt silicon carbide MOSFET, 300 amp against IGBT, and if you cause a short, and you can see that the short circuit current for this power module specifically, it rises 4 times for IGBT. That gives you enough time, 10 microseconds, to interrupt that fault before the device explodes. While if you get the same current rating silicon carbide, in 2.2 microseconds you have to interrupt, the overcurrent can reach more than 10 times the nominal current. And you remember the chip is much smaller, right? Thermically, become a nightmare, and that's the reason why it breaks faster, right? And that's become a big challenge how to overcome this, because you have to identify this fault and interrupt very fast. And normal DSAT techniques for the gate driver is not suitable for, especially for high power silicon carbide. So you need to have something different. Yeah, that's what I say here. And then also your colleague showed Rogowski, and Rogowski is also one of the techniques that we investigated in the past. You can put around the conductor a current transformer, right? Like where the Rogowski, where the output secondary is proportional to the DI/dt. When you have a low impedance short circuit, the DI/dt is very high, and then the voltage becomes high. And if you integrate this, you can have an image of the current, and you can just compare to a level, and eventually you can tell the gate drive to interrupt whatever it is. And these will be only meaningful when you really have a very high DI/dt. And that's what we did as well for this power module. We put some Rogowski coil in the terminals, and then we can predict what is the current. So in this case, we set a trip margin of 100 amp, and then we reconstruct the current. As soon as it goes more than 100 amp, we ask them to trip. So what we did, we switch on in a half bridge, first one MOSFET, and eventually, after some time, we switch the other one on, and then we cause a short circuit. That's exactly after the green curve goes up, is when you switch both devices at the same time. And you can clearly see the current rising very fast as the yellowish. And then when they reach the trip limits that we set it in the comparator, you can see the protection, the purple going high, and in 200 nanoseconds after that, the gate start acting. So you can clearly see, and then we do soft turn off, right? Because we don't want to have over voltage. Then we intentionally make it not so fast, right? So make the device go into linear region, where the impedance of the device move from zero, very low impedance to high impedance, but slowly. So then we don't cause over voltage in the device. So very fast you can do, and for this module, as you saw in the previous curve, you have to open in less than 2 microseconds, and then we can open this already in that 500 nanosecond margin for the instant of the fault, right? And the detection can be faster, can be in the range of, we could set up to 50 nano, but that would also cause a very high over voltage, because this package has a lot of parasitic inductance. Yeah, another key challenge when you put in a power module, or if you use discrete devices, is in application like EV, there is a lot of cycling of the module. And then you can see here, if you take a thermal camera there, you see some devices are hotter than the others, right? And that can cause thermomechanical stress. And especially this thermomechanical stress, if you use wire bond into the thing, then they degrade the soldering, and eventually there is wire bond lift. Also, the soldering of the device is also degrades over time because you have this swing of temperatures, right? And that's caused a lot of thermomechanical stress. And that's one of the key issues, especially if the chip's area is very small. That's the reason these new modules, they don't use wire bond, right? They use bus bar type to avoid those things and to make it more reliable. And the application like transportation is very critical for that, right? Because it's very rare you have continuous power. You are really fluctuating all the time. And that's where you see huge development from conventional power modules to more complex molded-based module, where you not only improve the parasitics, as I said, when there's a fault, you cannot interpret immediately because if you do that, it creates over voltage, right? You cannot have a high DIDT interruption. We also have to have soft DIDT, otherwise you create in the parasitic inductor over voltage. And you also need to make sure that we can extract the heat out of it. So that reason we have a lot of compromise between electric performance and thermal performance. Yeah, that's what it says here. Another area that we also study is really this using sensing to predict degradation. We talk about wire bond lift. If you have wire bond lift, the impedance of the device increases, right? So if you are measuring constantly when the device is on, the impedance, the RDS on, let's say, if there is any degradation, this RDS on eventually increases. If there is an increment of RDS on over time, then you know that the device is degrading. So you can already do preventive maintenance, replace it. So if you have sensors for voltage and currents and also thermal, you can already, by knowing how was the performance in the beginning of life, and then you know, right? So this is what they call intelligent gate driving, typically. And then we can have the state of health prediction of the device or the packaging. Yeah, this is also a key area in power electronics. And of course, as I said before, different circuitries, different modulation strategy, different devices, different materials, different cooling performance, different applications requires a quite understanding of different technology to be able to, for each application, you design a system to select the optimal, right? So multi-objective optimization, especially these days with AI that help you to really go in depth, analyze systems more closely, it really helps you in the design space to select what's more meaningful for you. Again, there's never a best. There's a best for a need, right? The best is always whatever the customer wants. If you can reach that, and to reach that is very difficult because each application has different metrics that you need to check. In terms of metric, you talk about the components, we talk about efficiency, weight, volume, failure, cost, There are different metrics that you need to design. Each application has its own. Also for system perspective, because the lifetime performance is also important. We talk about total cost of ownership. You want the running cost to be low, maintenance to be low. Efficiency, cost of energy, it has to be low, right? So then there are different metrics, not only thinking about the initial cost or initial life for the component, but how that component be used and how it's going to be used out affect the whole lifetime of the system. So everything needs to be taken in consideration these days, from circuit to system perspective. And if you compare different applications, you see different metrics, which for industrial applications, normally cost is relevant, but efficiency not necessarily. Reliability, you can also replace relatively fast. But if you go to transportation, aerospace, cost is not relevant so much, but reliability is. Efficiency also is important, especially weight in aerospace, right? So then different metrics for optimization give you different circuitries, different materials, different everything, right? So understand this is a core of a power electronic engineer, right? It's really, I believe that we are really a designer, right? We are really integrator of technologies. Good. So think about the trends for EV application. First of all, you know that pretty much all means of transportation become more and more electric, right? Battery especially is the enable technology for most of those, right? So you see here, nowadays, you see more electric bikes than normal bikes. It's really moving the technology. And that's because battery is improving a lot as well. And the cost of battery is reducing as well. And of course, we want less CO2 emission. There's also a strong governmental push for it. And battery, it is on the rise together with power electronics. Another trend is, you think for the perspective of the charger of batteries, there are different technology, right? So we have for EV onboard charger, where the power electronics is inside the vehicle. We also have the off-board chargers. The onboard charger, because you want to limit space, eventually there is a power limit that you have there, right? Normally, also your public outlet only allowed you, if you are lucky enough that they give you up to 22 kilowatt plug. Most places give you maximum 11 kilowatt. So eventually the onboard charger, most of them are going to be 11 kilo to below. But if you want to charge faster, then you need to use a public charger where the power electronics is completely off board. And some of them goes in up to 350 kilowatt, right? But we also have wireless charger where the power electronics is partly outside, partly inside. And depend of the application, we also have the battery swap, where a little robot comes and replaces a depleted battery to a new one. And this is done mostly in fleet. If a company owns a fleet and own all the battery, then it's okay. But for you, that if you buy a new EV with a new battery, you don't want to get an old battery implemented, right? So for you, maybe not going to be very interesting. But anyway, all these technologies, they are different, but they're going to coexist. And I'm going to take a look in this, before that, the power electronics of this. Actually, the power electronics is very similar, independent which technology is. The most dominant ones are the two-stage system, where you have a rectifier and a DC-DC converter. And the DC-DC converter, typically where the galvanic isolation that is required by the standard is implemented, because also you want a compacted system, especially it's on board, right? So you need a medium frequency transformer there, right? So isolated DC-DC topology is typically used. And what happened now here is that because you connect to the public grid, you need to have power quality there, right? So then the rectifier deals with the power quality, make sure that the filter is properly designed, that you have high power factor operation, and the DC-DC converter is responsible for the charging that's needed. So the BMS informs the charger what kind of current profile you should inject there, and who will handle that is the DC-DC converter. So that's the DC converter is very, very, very important for the customization of the charging, because each car, they have different charging, right? And the AC/DC deals with the requirement from the public grid. Regarding the different charging technology, take a look at the maritime. A maritime vessel, they also have onboard charger, right? So then, because the power is relatively high, you can go and put AC cable there and then you can charge your car, your ship with the onboard charge they have there. But they also have off-board charge. If you really want to charge in megawatt range, the cable is so thick that you need a robot to come and connect. And that's what this ABB robot arm charger. And that's happening sometimes in buses as well. And you also have a lot of battery swap there. So a crane come and just replace the battery pack. It depends what kind of vessel it is, depends how often they come to shore and leave, right? But also they have wireless power transfer, right? So Vassler also implemented this megawatt charge for some of the ships. There is a robot arm that positions the coil. So when the ship cannot be closed to there, then you can have this robot that can position and charge the ship. And I don't know if you know, but although you can have diesel generation, and most of the ship has diesel generation, but you cannot use the diesel generation close to the shore. You have to use batteries there, right? That's why battery is very important in this, and that's the reason why most of the ships are electric, right? Now, another trend you see is really the increment of charging capability. Nobody wants to be waiting hours to charge your EV, right? And there are key applications that weight is not an option. So what you see here is the charging equivalent to the C rating of the battery they own. You see that little truck, the big truck there that goes to 6C, those are mining trucks. So those, if you wait there, you lose a lot of money because mining is a huge business, right? So they really go up to 6 megawatt charging for a truck. I know ABB because my colleagues work on that, and they're developing medium voltage battery packs with 6 megawatts for this application. They are really hungry for power. Maritime, because of reliability, you don't want the battery to degrade, then you really charge at very low C ratings. But the power, because the battery pack is so large, is very large. You have 10 megawatt chargers. The key problem, as you already saw in before, if the power is too high, the current is too high, then the cable is not easily maneuverable, right? So there is a tendency for high power application where the battery pack voltage increases. Because for the same power, the current drops, right? So there is a huge push for series connection of batteries. Yeah, so if you go this. Another trend is what they call power electronic building blocks, right? So you see there are so many markets in the EV. Every manufacturer produces building blocks. Although they deliver 350 and sometimes even megawatt, they are building these little blocks with up to 50 kilowatt. So especially we discussed already for the DC chargers, most of them may need only 50 kilos. So then if you have already just a building block of 50 kilo, then you can already have a very compact wall-mounted DC charger with 50 kilowatt PEB, right? And that can be paralleled up to megawatts. Yeah, so there is a lot of products available. If you Google it, you find many. I just give you here 4 examples. As I said, the trend of increment of battery voltage is also related to the end that you have, right? So common cars, today they use 400 volt batteries, and they will continue using 400 volt batteries. Nissan Leaf, Tesla Model S, they're low cost EVs, right? But if you go to the high end vehicles like Porsche Taycan, Aston Martin and others, then you start seeing 800 volt batteries. Those are large battery packs, and they want it to be charged very, very fast. So that means they go to 800 volts. So in a way that your plug can still be maneuvered by you. It doesn't need a robot to do it. But now you see BYD, they really push the limit, and they're already going to 1,200 volt battery packs. And then they can charge very, very, very high for the semi-current limits that you have in the plug. So you see these 3 voltage classes most likely going to dominate, and it's always multiple of 400 volts, right? You can clearly see. Yeah. So the problem is now, how can I charge efficiently 3 different battery packs? And that's a key challenge for power electronics, right? Because you have public charge, you should be able to charge everybody, right? That's why you have a lot of standards like ChargeMore and ChargeG, that the charger should be able to supply from 50 volts to up to 1,500 volts, which is exactly the range of the low voltage charging, right? And this wide range makes the design of the DC-DC converter very, very, very challenging. Because most of these topologies, restaurant type, phase shift converter, they are buck type topologies, right? So then eventually, peak efficiency is always at the highest voltage. And then if you have it, the peak efficiency at high voltage, where you can supply a BYD, how many people are going to be in the world have a BYD like that? Not many, right? But how many people are going to have a 400-volt car? Far the majority. But if the efficiency of your charger is the lowest at 400, that's not good, right? That's a problem. Another challenge here is the spectrum of the electrification. So if you go to a port, you need the cold iron to charge your ship while they are mooring. But it's not only that. You need that energy to be from renewable energy, right? So you need wind, solar close by. You need battery packs to establish the congestion. Also in the port, there's a lot of cars, there are buildings that need energy. So the whole thing there is like a huge microgrid that's quite power hunger, right? A lot of different vessels, not only large ship, but also water taxis, straddle carriers, terminal tractors, forklifts, and so on and so forth. So each of them are also being electrified, they use batteries, right? So they need to be charged, and that's why the voltage range of the charger is really from low 50 to 1500. Yeah. And depending on the power, you need also connection to the medium voltage grid. And it's make the power electronics also very complicated, right? So that's one example of how you see the charging. Most of the, so you have the medium voltage grid, then you have a transformer to bring to low voltage, and then you have the two-stage chargers. And then you can see different vessels, they're going to have different power, and you can already see the conventional 350 kilo that you can find more and more often in Europe. They'll be charging buses and cars. But if you want to really charge large vessels, then sometimes you need direct connection to the medium voltage, where solid-state transformers may be used. But also, if the installation is far away, you may need not a medium voltage DC distribution. We have the MMC type to bring from medium voltage to medium voltage distribution, higher voltage, right? Then you bring back to the medium voltage, but lower voltage, medium voltage. And then you again put the two-stage chargers and solar, blah, blah. And yeah, so you see in such installation, you have so many electronics, so many different technologies, and all of them eventually going to coexist. Now, the other challenge is the degradation of the battery, right? So the battery is, if you start charging very fast, eventually, again, like for the semiconductor devices, the materials also, losses create degradation of the materials, right? So then you need to be very, very, very careful. Yeah, so the push for high voltage is there to really increasing the charging, but also the higher voltage battery packs are also less reliable because of the voltage sharing, right, of series connection devices. They degrade differently, as we're going to see in the next slide. Yeah, so these are the trends I see for the application that we work on it, and those are how we leverage our research. We try to use the potential of the semiconductors or limitations of the packaging and so on, and then try to adapt to the needs of the application. And we work pretty much in all that layers, from solid-state transformers to AC-DC connection to the DC-DC topologies. Yeah. Then I will show just two presentations, two research areas that we did it. One, to solve this issue about different voltage class of the battery. How can we make it, the DC-DC stage that is responsible for the charging, efficient for all battery packs? I mean, it's not only us doing that. There are people doing that already. Yeah. So ABB had a patent already beginning of 2000, where they have a switch matrix. So as soon as you have two systems or three systems, you can put mechanical switches that can connect the DC-DC converter in series or in parallel. And then you can already, if you have a battery 400, just use all the converters in parallel. And if they are 800, you can put two in series and so on. So that's how they do. The issue is mechanical switch. They have limitations, how much you connected. In the charging, of course, you can always turn on and turn off at zero current, right? Because you don't need to initiate the charge before. You can switch on and off the matrix before you start the charging, right? Pretty much. But eventually they are not as reliable as semiconductor-based switches, right? So people start to think about how can I change the DC-DC converter, right? So this is a solution that has been proposed also quite recently, where you can use the full bridge. In this case, we have a dual-active bridge, operate a full bridge in primary, full bridge in secondary. But if you wanted to have half of the voltage in secondary, what you do is the primary side, you just operate in half bridge, and you move from dual-active bridge to a resonant converter. And then you don't have a saturation with the transformer because you have the capacitor there blocking the DC component. And then there's a way that you can charge two different voltage classes and still be efficient in a way. So you can also use a tap, electronic tap in the transformer if you wanted. So you can have a secondary side there that you can connect it only half of the winding or the complete winding. So then you have a gain of the transformer there. The problem with the solutions is the component is not fully utilized, right? So if you think about the first case, if you operate from full bridge to half bridge, then one of the legs not used at all. So then you have a device that costs money and you're not using it. And also the switch that you have there has to, for the same power, have to have twice the current capability, right? And that's also another problem. So what came into the market in the end, that's also a patent for ABB. I was using the Terra 50. So what you can do here is you have two transformers and you have a network of devices. There's the diodes there. Depending how you operate your primary full bridge, if you operate in phase or in antiphase, you can have the diodes conducting the secondary differently. So if the primary side that can be connected in series, in that case is connected in parallel, but can also be connected in series. If you put them in phase, then the D11 and the D31, the middle diode doesn't conduct. You just use the other one. And if that happens, both secondary sides are connecting in series. Then you have the double gain. If they're in antiphase, the windings are connecting in parallel. So then you have a gain 1. And then what you do there is, you have a double gain. And the advantage of this topology is the current ratings in the primary side doesn't matter in relation to the configuration in the secondary side. You still have the same current, so you have a high utilization of the semiconductors. So it's a huge advantage compared to the previous solutions. There is also another option that using solid-state switches instead of mechanical switches, where you can put two secondary sides in series or in parallel using solid-state devices. So you don't have the issues of the mechanical switches. It's an improvement from the initial ABB patent. And again, you can do parallel or series connection of the voltage source. Also work well. So what we did here, because this is very good for 2 battery packs, right? If you try to do three, the mechanical switch becomes very inefficient because you need the number of mechanical or semiconductor become too large and it becomes very inefficient. So we thought we combined those 2 classes, and this is the PhD of Soeiro. So we did like this with 4 winding transformer. We can do now different configurations. So we can connect it, all the secondary windings in parallel or in series, in that case, in the first case in series. So then we have all transformers in series, so we have the large voltage gain. You can connect 2 windings in series, and then they are connected in parallel, in module 2. And module 3, they are in parallel and in series, and then the module 4, all of them in parallel. And then what you do that is, independent which mode you are, the primary side, the utilization is still the same. So we are fully utilizing the transformer and fully utilizing the devices. Only some of the diodes are conducting, some of them not conducting, right? And then you can clearly see there are 4 states possible, but module 2 and module 3, they create the same voltage. So you can use mode 1, 2, and 4. That's the best ones for the conduction losses. So that's the stage that we use. Yeah. And then you can see here in Soeiro's prototype that for a given current, we just fixed the current, and then we charged the different voltages. And you can clearly see there, for the higher voltage, we have the high peak there. The red is a resonant converter, so we have different quality factor. Higher the quality factor, higher efficiency for resonant converter. But that's, at the moment, not that important. What's important is that what you have there is a reset of the efficiency, you see? When you, in operation mode, as I said, they are buck-type topology, the peak efficiency is always as the highest voltage. When you drop the voltage, you also drop efficiency. But then when you reset, when you change the operation or the configuration, the efficiency goes back to what it was, right? So now you can have, and you can see if you are using a resonant converter to charge the whole thing, you can see the line there. It will be the same efficiency as the higher voltage, but then when there's configuration for 800 volt or 400 volts, you see the efficiency drop is huge, right? That means this reconfigurability is very good. And you can see most of the cars going to be 400 volts. So if you have a charger with a single converter unit, then you'll be charging always, or let's say 90% of the time, at the lowest efficiency. That's not good, right? That's why the reconfigurable topology for chargers, and that's why ABB was investing in the technology, in the initial technology for 2 batteries. Now more battery comes, and then more reconfigurability is necessary, right? Yeah, so yeah, I see such a solution like Soeiro, and there are different ways to operate that. You can make it in different ways. You can combine many other reconfigurability techniques and implement in similar way. Yeah, seems to be the future. Battery degradation. As I said, there's a push for series connection of cells, right? And in this test here, they cycle 48 cells, and they saw that some of the cells, they reach end of life much faster than the other, and they are from the same manufacturing batch, right? So some of them, they define the end of life when there is a drop of capacity of 20%, and they saw that the first cell to die was in 900 cycles, and the last one to die was in 1350 cycles, right? So now imagine that you use these 48 cells and put them in a string, right? So eventually, the string will die with the first one, right? And that's a big problem when you put device in series, because then you are not necessarily going to, your total cost of ownership will drop, right? Because the weakest link is going to give you the performance. And that's a big problem, right? And then typically the degradation appears in the impedance. So by measuring the impedance of the cell, you know if a cell is degrading. So by measuring the impedance, you know the state of health of the cell. That's the reason Prashant will show most of the way that we predict state of health is by measuring the cell impedance. That can be measured with the power electronics as well if you incorporate some smart BMS. Yeah, and you can see the series connections. What happens there? Some is the voltage, right, and time. You can see some of the cells have, because the impedance change over time, they're going to have different voltage stress in a string. And that's why they're going to degrade it different. They have different losses. Also, if you have parallel connections, also, especially during dynamic stage, you also have different current sharing. And that's why when you make really large package, become challenge. And that's what the research for Rehani. So the idea is bring power electronics close to the battery modules, not in the cell level, but really sub-modules level. Sub-module of 48 volts, for instance, where they have a series string there as well, but yeah, at least lower voltage. And then what we did here, we did based in the MMC based, or cascade HP based, we have 2 cascades in series. And then we can use bypass or insertion of cell to create two voltage sources, and these 2 voltage sources can be used to control the current in the AC side. So we can control the charging or discharge of this battery like a normal 2-stage system. So it's like a 2-stage system. And that's what it is, how we operate, right? So the upper string can create a voltage, controllable voltage, the bottom one as well. And then with the rectify stage, you can just control the current because you can control the terminal voltage, right? And you have control of the current in the inductance there, right? then you can inject or absorb current. And the advantage here is if we implement impedance measurement into the sub-module level, you can insert or bypass cells that are weak, right? Because it's a modular, series modular. For the same voltage level, we have multiple options, right? So you can insert the cells more often, the ones that are more lifetime, compared to the one that has less lifetime. So then you can extend the whole package lifetime a lot. The challenge here is that what Johannes did it. It's not only measuring the impedance of the module, but also what happens if you have asymmetric voltage, because different state of charge in batteries means different voltage insertion. And then for controlling the current in the AC side become a challenge. And you start to see distortion in the current, right? So you start to create reactive power there, and the power quality gets problematic. So, but if you can use asymmetric modulation, you can improve that performance of the system. You can see we want sinusoidal current there, right? So you, in the primary, if without the modulation she proposed, the current was a little bit distorted, but then when you do the asymmetric modulation, it becomes more. And additionally, as I said before, low voltage devices have better performance, right? Now we have also this multi-level operation, right? You can see that the steps. So we can have smaller filters for the power quality, but we also can have better efficiency. Yeah, it's nearly finishing. So this is topology from Soeiro. You can use this topology to also, before as a resonant converter, you can also do a dual bridge converter if you want it. You can also do a phase shift converter if you want it, because it's not the technology is not dependent on the DC-DC technology. It's just the reconfigurability, right? And because those topologies always use full bridge or half bridges, they can be extrapolated to any technique. But we discussed about solid-state transformer, right? Solid-state transformer is a combination typically of a cascade H bridge for the rectifier stage and a DC-DC converter, right? Then you can also use the DC-DC converter to build directly medium voltage connect battery chargers with high efficiency for much battery voltage with high efficiency. So you can extrapolate that to solid-state transformers. You can also use for directly AC-DC converters, right? So you can also use GaN-based, if the 4-quadrant GaN that's become very popular these days. And then you can make a very compact, because GaN will be medium to low power, right? Chargers for shopping centers or anything like parking lot, maybe up to 50 kilowatt DC charger, which park really bad, but it could be very thin, very small because it's GaN-based. And it's a medium frequency transformer, right? So it's a directly AC-DC with isolation, right? So then it can be very compact and versatile. This is actually a topology that I and Professor Bauer proposed. So Bauer is from Slovakia. You know him, right? Yeah. And Rehani topology can also be modified the front end using what they call quasi-multi-level concept, that you can replace the T-type or Vienna type front end with series connection of low voltage devices. And then we can have advantages in efficiency, conduction, and switching losses and make the system even more efficient. Yeah, this is the future research we are planning to do. So as a summary, as you know, power electronics everywhere. Power electronics evolved from semiconductor technology, so we use the feature of the technology to do research in circuitries and modulation. Battery is in the rise, is enabling transportation. And transportation is enabling battery because the volume is large, the cost reduces, become more affordable, we can afford electric cars. Plug is a limit, that is high voltage because of current, that is a high voltage battery become necessary. And that's why wide band voltage is necessary, it complicates the charger, and that's why the DC-DC converter need to be able to withstand efficiently all these battery classes. Yeah, different infra gonna exist. You're gonna have job for everybody, I think. There's a strong trend of power electronic building blocks to give you advantages, right? Commercial advantages. Yeah, the back-end converter needs multifunctionality. This reconfigurability, I think, is a high, interesting topology. As I said before, ABB already was doing that in the first generation of DC charger, the 50 kilowatts Terra that was already using that reconfigurable solution. Yeah, this split battery that Rehane was doing, I think, give you flex management of the charging, extend or improve the total cost of ownership, make sure that your battery is fully utilized, and yeah, improve both the system performance, the component performance, but also system performance. That's it.